Okay? So now we got to do the dot product. Right? Now we got to figure out what is the work that it's doing. These lights are on. Okay, so the work we know. Then we have to go to our work formulas and decide which one we're going to use. Remember, there were three. There was if the force is constant. Let's see, if the force varies, you do the integral. If the force is constant, you can just do the dot product. And if they're the same direction, it's just F times delta R. But here they are different directions. Now you can see it. There's the force up. There's R that way. The direction is not the same. So we have to do this one. Work equals the force dotted with, if I called it R, delta R, R. Yeah. We have to do that dot product. Okay. So I'm kind of torn in this class. We don't really push you really hard on complicated vector problems, but then also I don't want you to wonder what a dot product is. So we kind of need to go somewhere in between. So I mean, the dot product it's usually described as the component of one vector along the other. Okay? So if we look at it it's F dot R. So we could say what we mean is here's R and here's F. And it really just means if you were to break F into components in the xy coordinate with R, right? So this would be one and this would be another. Right? You could do that because this is 90 degrees. You can break F into 90-degree components at any angle you want. So let's do it where R is like the x. So this is F parallel to R, and this is F perpendicular to R. Okay? So the dot product is just a way to get this. Gives this, F parallel. That's all the dot product is. Two vectors, you want the component of one along the other. Dot product. Mathematically, it's equal to the magnitude of F times the magnitude of R times the cosine of the angle between them. Yes. Let's see. So in the end, that's then the answer. That's what the work is. In this case, if we move the thing up that, it depends. Let's see, F, the magnitude of F is mg, and then R and cosine of theta, where theta is the angle between F and R. So there would be your theta. So if this were a mathematical problem where I told you where A and B was or something, you would figure out the angle, and this was the answer to the question. What's the work by the hand from A to B? Right? But let's think a little bit more about this, what this really means, because oh wait, no, that's later. Hold on, sorry, I'm mixing up my slides. Hold on, this is much later. Or no, maybe it's now. Sorry. No, it's now. Yes, it's now. Yes, it is now. Okay. Please explain the picture again. This one. So I put what's the component of F along R? It's F parallel. What's the component of F perpendicular to R? It's F perpendicular. So I'm just breaking this into two components, just like if I had it in XY. If I had this force in XY, how would you get the components? F cosine theta is the x component. F sine theta is the y component. That's all I'm doing here. I'm just taking my head and going like this. All right? So we turn our head, and then this becomes fx, the parallel. We call it parallel now because it's not in x. It's parallel to r. And perpendicular to r is the new y. Okay? Okay, so one thing interesting about the dot product is it's the way to multiply two vectors, and you get a scalar. We get an energy. But this isn't really the physics way to think about this dot product. It's F along R. Can we think about it as R along F? Along F. Can we think of it, is it okay to think of it that way? And the answer is it's actually better to think of it that way. Oh, Lord, let's see. This is what happens when I try to teach math. It's such a bad idea. Oh, yeah. So, I'm not going to tell you the math of doing the dot product. There's the Cartesian coordinate way. We don't need to do that. That's what somebody asked about. Okay, so we could also think of it this way. Is it R along F? So the question sort of is F dot R equal R dot F? Do you get the same thing? Because we could say if the force is up and R is like that, could we call this, no, I don't want to think about the forces component along R. I want to think about the component of the motion that I moved along F. And the component, this is getting hard to draw. It's easy to draw. The component I moved perpendicular to F, right? So there's R, and this is R parallel, and this is R perpendicular. Okay? This should be the same thing. And the question is this true? This is called commute. Does the dot product commute? Does anybody want to shout out yes or no? Does the dot product commute? Yes. Why does the dot product commute? Well, one is the component on the other is a component on the other. So, okay, that was good. Let's think of another reason. Because cosine is symmetric. Ooh. Right? If you were to say r dot f and f dot r, then you would say this is 10 degrees and this is minus 10 degrees. Or 30 degrees and minus 30 degrees. You know, it's the angle from f to r. That is clockwise, negative angle. The angle from r to f is negative, or is counterclockwise, positive angle. So it's kind of like you're switching the sign on the angle, right? But let's look at cosine. What is cosine of 0? See, you have to intimately know your sines and cosines. I mean, like, just walk around all day. Yes, it's 1. Very good. As soon as you know it's 1, you're done. It's the one that does this. Oops. Oh, Lord. Intimately. Except when they go negative. There you go. Cosine looks like that. What does that look like around the origin? It's symmetric. Cosine of 10 equals negative cosine of 10. Cosine of 90 equals 90. Cosine of 45 equals minus 45. Right? It's really mathematically, because cosine is symmetric, that actually f dot r equals r dot f and it commutes. But the physics part I'm wanting to talk about is when we're talking about the work done, we're really talking about the potential energy that you're giving it in this case. Right? I didn't speed the ball up. I moved it to a higher level. So the work didn't go to speed it up. The work went to increase the potential energy. So now you're going for bonus points. Right? You answered the question. But now also, what did you do with the work? The work increased gravitational potential energy. And what I'm trying to do, very confusing, is one, talk about dot products, but also talk about this idea that what matters in terms of gravitational potential energy is how high you go. It doesn't care how far you go. It cares how high you go against gravity. Right? So if you think of it as the component of r along f, and f is against, f has to be straight up, then it's going to be how high you went. So physically, it makes more sense to say how high did I go against gravity, not how sideways did I push along r. Right? That's not as good. It's how high you went against gravity. Okay? That was way too much time on that attempt to clear that up. What do you mean when you say r commutes? This is just the definition of commute. If a times b equals b times a, it commutes. Okay? The cross product. Has anybody ever heard of the cross product? We used it with torque. Remember when we said torque equals r f perpendicular or something like that? We said that, right? What we really meant is that the torque is the cross product of r and f. Okay? And this doesn't commute. Cross products equals minus f cross r. You get a negative sign when you switch the order. That's what commute means. This is also why cross products contribute to global warming. It's because they don't commute anyway. Yeah. Okay. Now you look horrified. You went from confused to horrified. And now I forgot what I was talking about. Okay, so now we're done. Okay, so anyway, I was just trying to clear this up. I think it was, let's not talk about that anymore. Okay? So lots of things there. Intuition, dot products, thinking about moving against a gravitational field. That was all illustrated. It'll all be in the exam. Okay.